Hello, I'm Lou Bloomfield and this is How Things Work. Today's topic, water distribution. Like everything else in our world, water exhibits inertia when it's at rest. It tends to remain at rest. When it's moving, it tends to continue moving at constant velocity. Water can accelerate so that its velocity can change with time. It can experience gravity, so it has a weight. What makes water complicated, though, is that it has no fixed shape. And you can actually have different parts of the water moving differently from one another. So watching water flow through plumbing is a little complicated. Instead of pushing on it with forces, we'll push on it with pressures. And instead of dealing with the overall mass of the water we're encountering, we'll deal with the density of the water, that is the mass per volume. So we're going to pay a lot of attention to little drops of water moving through the plumbing. And we'll try to look at how water goes from the water company or the water tower through the city plumbing to your house, and in through your house to the shower, to the sink, and so on. Okay, first observations to make about water is we want to start simple, so I'm going to leave gravity out of the story initially. And a way to do that will be to consider plumbing and water flow only horizontally. Nothing's going up or down, so there's no gravitational potential energy and no weight to worry about. One other issue that I'll do for the entire story here is to omit a friction-like effect that tends to mask water's inertia. That friction-like effect is actually associated with what's called viscosity, the syrupiness of water, and in fact every other fluid, with one notable exception really. Fluids exhibit viscosity, they don't flow perfectly. So it's, in reality, if you get water flowing through a pipe, it won't perfectly coast, it will gradually slow down because of these viscous effects, but that's for another day. So here we are, horizontal plumbing, no viscosity. What goes on with water? Well, if the water is moving, it will continue moving at constant velocity. So if you have a straight pipe running from way off to the left to way off to the right, and you don't push on the water, it will, if it's motionless, it'll stay motionless. If it's moving, it'll continue moving steadily through that pipe. How can you change this? How can you make it so the water accelerates? Well, the way to do that then is to look at the pressures at the two ends of the pipe and make them different. If the pressures are the same on both ends of the pipe, then the force exerted on the two ends of the slug of water, the cylinder of water that's inside the pipe, those two forces are identical. How do we know that? Well, if you take the pressure on this side times the surface area of that cylinder of water, that gives you the force on the water. Pressure is force per surface area, and then you multiply it by the surface area, and you get the force. If the forces are the same on both sides, that cylinder of water in the horizontal pipe is experiencing zero net force. We've got gravity out of the picture. It's downward and the pipe is supporting the water. We can ignore gravity. All that matters is the two forces on the end of that cylinder of water, they match, zero net force, the water coasts. Things are simple. If you change the pressure at one end, make it higher. So let's let the pressure at the left end of this cylinder of water increase. Now there's a net force on the cylinder of water, and it accelerates. And the acceleration depends on how much mass there is, and therefore on how long the cylinder of water is. So if it's a short cylinder of water with a certain pressure difference, it'll accelerate relatively rapidly. If it's a long cylinder of water with more mass in it, and we could do the mass by taking the density and multiplying by the volume of the pipe, details I will not pursue. If it's a long cylinder of water, it won't accelerate so fast. Most important thing is water accelerates in response to pressure imbalances, and it accelerates always towards the lower pressure. And this is familiar. You take a bottle of water, you pressurize it by squeezing the bottle of water, and pull off the lid, the water sprays out. It's accelerating from the pressurized region that you've created with your hands to atmospheric pressure outside, which is lower, and it sprays out. So that's one way to pressurize water to cause it to accelerate. Well, suppose you want to accelerate the water, get it moving, and then get more water and accelerate it and get it moving. You probably then want a pump. So if you're going to pump water steadily across, you're going to want to pressurize the water, deliver it, pressurize the water, deliver it. That's what a pump does. Looking first at the idea of pressurizing water, take a moment on that one. If you start with a volume of water, for example, a water bottle, you can make a pump out of a water bottle. It's not going to be very fun, but you can do it. So you got a 1 liter plastic bottle of water, and you seal it and you squeeze the bottle. When you squeeze the bottle, you push inward on its skin, and the skin will move inward unless something accelerated inward, in fact, unless the pressure inside rises to balance you and reach a new equilibrium. And that's what happens. You squeeze on the outside of the bottle, and the water inside experiences a rise in pressure to stop the walls of the bottle from accelerating inward. So now you've got a higher pressure in the region around where you're squeezing, and actually that pressurizes the entire fluid when you do this. Whether you squeeze on this spot on the bottle or that spot on the bottle, doesn't matter. Any spot on the bottle, if you push inward on it and force the water locally to rise in pressure, the whole bottle's pressure will rise. That's an example of what's known as Pascal's principle. And Pascal's principle observes that if you've got a fluid that is incompressible, and water is an example of an incompressible fluid, meaning that as you raise its pressure, its volume doesn't change. In reality, water's volume gets a little smaller as you increase its pressure, but so little nobody will notice. So it's an incompressible fluid, as opposed to a gas which can be compressed. You can pack it tighter. Incompressible fluid, when you squeeze it in, the pressure, if you change the pressure at one location, that pressure, the pressure changes the same everywhere in the entire enclosed container. So pressurizing one little piece of the bottle pressurizes the whole container. All right, so you've done that, you've squeezed the bottle, you've pressurized it. When you open the lid now, the water, which is at high pressure, will accelerate toward lower pressure, and the water will begin to flow out. And as that happens, you will have to keep pushing inward to keep the pressure up on the water. As you deliver water, you have to chase it to keep it under pressure. And that act of pushing inward on the water as it moves inward involves work. It turns out that pumping water, which is to say pressurizing it and delivering it at elevated pressure, takes work. And a simple example, do I have a syringe around here? Didn't plan ahead. Well, I can get a bottle here, just show you. So as I push, here's a bottle. If I squeeze inward, it doesn't have any water in it right now. So I squeeze inward, I can keep delivering pressurized water. And if you've ever played with one of these bottles, you know that you keep squeezing as it keeps squirting water. You're doing work the whole time. And the amount of work that you do turns out to be related to the volume of water you deliver and the pressure at which you deliver it. In fact, it's the product of the two. The math of that I'll leave for the book. But it turns out that you can do work in different ways in different contexts. We learned long ago that you do work mechanically. The simplest approach is to exert a force on something and have it move a distance in the direction of your force. That's the first rule for dealing with work. There's a second one, which has to do with rotation. If you twist something, that is, you exert a torque on it, and it rotates an angle in the direction of your torque, you also do work on it. And here now is a third one. If you pressurize fluid, you push inward with pressure on a fluid, and it moves a distance in the direction of your pressure, you do work on it. And the amount of work you do in this last case is the pressure you exert times the volume at which volume of fluid which you deliver. So pumping water, particularly at high pressure and at high volumes, involves a lot of work. And this is a real issue. Water pumps consume a lot of power as they deliver their water. The more water you take out that's delivered by the pump, and the higher the pressure the water has as it leaves, the more work the pump is doing. So big water pumps that deliver a lot of high pressure water are very high powered pumps. So when you go, for example, to a water pumping station, or many amusement park rides that involve water also involve big pumps, and you can see the motors that are driving those pumps are as big as trash cans. They're huge motors that are consuming tens of thousands of watts, delivering high pressure water at great volume per second. Okay, so pumping water takes energy. The water then carries the energy with it, and that energy can do stuff. A lot of the parts of ordinary household plumbing allow you to see that energy. For example, a shower. When water comes out of a shower head, it's moving fast. What gives it the energy to have that big kinetic energy that it has in order to move fast? Well, that was the water pump way back at the water company. They put the energy in. You're seeing it in action. Or when the water a toilet that doesn't fill a tank with water, but rather uses the water pressure to run the toilet. When you flush the toilet, whoa, there's a huge movement of water, very fast, very powerful. What propels that? Well, it's again the energy put in by the water company. All right, can we sort of watch that energy in action? And the answer is yes, and it's really enlightening. Watch the energy move through the system. You learn a lot about the system. So let's watch the energy moving through plumbing. And still, I'm dealing only with horizontal movement right now. Gravity's still not in our story. And as water moves through a static plumbing environment, which is to say, plumbing that's not moving, that's just sitting there, and that you can't see any movement in the plumbing. And furthermore, you can't see any change in the movement of the water itself. This is a situation known as steady state flow. So we're going to look at steady state flow, and just to make sure it's clear what steady state flow is. It's the flow of water, in this case, through an environment that is not moving. So the structures, the plumbing, no movement in them. And the water itself is doing the same thing every second. You can't tell that anything has changed because all the water is going through the system. It's replaced perfectly by more water. And the way I describe this finally is that you can't tell the difference between a movie of this situation and a still photograph of this situation. They look the same. All right, so that's steady state flow. And in steady state flow, where it's all horizontal, it turns out that there's a beautiful relationship between energies within this that makes things very simple. And before I tell you that relationship, let's watch a drop move through our static environment horizontally. If I start dripping in drops of water up here, so we get a peek at the movement of the water. Otherwise, it's just clear. If I put drops in, you can watch the drops move their way through the environment and go out the far end. And each time I put a drop in at the same location upstream, it follows the same path. And it maps out what is called a streamline. So if all the drops that start right there work their way through the exact same path and leave the same way, that streamline, it's different from a streamline I would identify by putting drops in elsewhere in the flow. So I'm going to follow that one. And the observation is this, that the energy per drop in that streamline never changes. So if it had a certain amount of joules in it per drop, it's always going to have that same amount of joules per drop. But that doesn't mean that the energy is manifest the same way at every location along the streamline. It can change. Between what? It can change between two forms in this horizontal movement. Kinetic energy, that is the energy of motion, and a second energy that's called pressure potential energy. The energy associated with pressurized water. Remember, pressurized water that's delivered carries energy with it. It takes work to deliver pressurized water. And in this circumstance, wherever you've got a lot of pressure in the local water, you have a lot of energy per drop in that water. So it's a potential energy. It's not a true pressure potential energy in that it's stored in the forces within the drop, but it works perfectly as a potential energy. The point ultimately is that as the drops along the streamline travel their path, they can exchange energy between kinetic energy and pressure potential energy, and vice versa, but the total of the two remains constant. So if the water along one of these streamlines speeds up, meaning it's got more kinetic energy, its pressure drops to compensate, and vice versa. So this allows for things like nozzles. When water goes through a nozzle, hopefully a nozzle is familiar to you as something you put on a garden hose, or as, in fact, as the tip of this. This has got a little nozzle at the end, a narrowing in the pipe. When water goes through that nozzle, its pressure drops and its kinetic and its speed increases. It's converting pressure potential energy into kinetic energy. And the total is constant, but one becomes the other. And you can predict then, given a certain amount of drop in pressure, you'll get a certain rise in speed. You can calculate it. And so you know, for example, you squeeze one of these bottles gently, the water comes out gently. You squeeze it ferociously, big pressure, the water comes out at great speed. All right, so that's a nozzle, and there's actually the reverse of a nozzle, a device in which the water slows down and its pressure rises. That reverse nozzle is known as a diffuser, and it's familiar, for example, on hair dryers. It's an adapter you stick on the end of a hair dryer to slow the air down so it doesn't like blow your hair into some sort of crazy style. You want to slow the air down, send it through a diffuser, which is a widening in the plumbing. The air traveling along the streamlines undergoes a drop in speed as it does this and a rise in pressure. So nozzles at one end can force the conversion of pressure potential energy into kinetic energy. Diffusers force the conversion of kinetic energy into pressure potential energy. Okay, so that's this observation that the total energy along a streamline, the total energy per drop along a streamline is actually a piece of what's known as Bernoulli's equation. Bernoulli's equation in all its glory observes that along one of these streamlines, the total energy is constant, total energy per drop is constant, and it's the sum of actually three different energies. Kinetic energy, pressure potential energy, which we've seen so far, and thirdly, gravitational potential energy. So let me bring gravity in. Suppose the plumbing isn't perfectly horizontal. Suppose it starts going up and down. Well, in that case, we start to notice that water has a weight. And furthermore, that water can store energy as gravitational potential energy by going upward, or release the gravitational potential energy by going downward. So now, as water flows through this static environment, we're sticking with steady state flow in this entire story. So as water goes through the static environment, flowing steadily along, it can convert its energy between three different forms: kinetic energy, pressure potential energy, and gravitational potential energy. And the sum is constant. So I've already showed you or explained to you that when water goes through a nozzle, it speeds up and it loses pressure. When it goes through a diffuser, it slows down and gains pressure. Now let's look at some up and down movements. If we send water up through a pipe, a pipe of constant diameter, so that the water doesn't change its speed, and I should say why it doesn't change its speed. If you send water through a pipe and force it to go upward, if it were to slow down, then it would create a traffic jam. The water that slowed down would get smacked into by the water that hasn't slowed down below it, and it would pile up there. And because water is incompressible, you can't do that. You can't. It's like a highway that's packed full of cars, if you come to a certain point in the highway and everybody slows down, it's going to back up the whole highway. You can't have part of the cars slow, part fast. On the other hand, if the water tried to speed up partway through its travels through this uniform pipe, it would leave a gap behind it. Same thing with the highway analogy. If suddenly you get to this point and everybody speeds up, they're going to start putting gaps between the cars. And again, water is an incompressible fluid. That doesn't happen. So water traveling through a uniform pipe has to travel through at uniform speed and therefore uniform kinetic energy. So in going up a pipe, the water can't change its kinetic energy. Instead, it's going to convert pressure potential energy down low into gravitational potential energy up high. It's going to lose pressure and gain altitude. And this is observed pretty often as water goes up a pipe in your house, for example, from the basement to the first floor to the second floor. We'll assume you've got a really tall house. To the 8th floor, right? You've got this gigantic mansion. By the time it gets to the 8th floor, the pressure will be pretty small. And if you look for things like, you go to a shower, try to take a shower on the 8th floor of this overly simple but very elaborate house, you will find that there's not much energy available in the form of pressure potential energy to turn into kinetic energy as it goes out the shower. So the shower will be pretty wimpy on the 8th floor. All the energy per drop is tied up as gravitational energy, potential energy. On the other hand, if you go down to the basement, there's not much gravitational potential energy there per drop, and therefore lots of pressure potential energy to become kinetic energy. So you get a serious shower in the basement, pitiful one on the 8th floor. Okay, that's water going up the pipe, so it's losing pressure as it rises. As you send water down a pipe, the reverse happens. It turns gravitational potential energy into kinetic energy. Pressure potential energy, think before I speak. And the pressure builds as you go down. And this is, in fact, this is the same kind of story we saw with the Earth's atmosphere. The pressure increases from way up high in the atmosphere to down low for the same reason. It's converted, you can think of it as converting gravitational potential energy into pressure potential energy. So as water descends from great height through a pipe of constant diameter, its pressure increases. And this is why we have water towers around. In water towers, you can have the water sitting there with lots of gravitational potential energy and minimal kinetic energy and minimal pressure potential energy. It's just sitting there in a big tank, top of the tank. Not a lot of pressure, not a lot of motion. But as it descends steadily through a pipe, it converts gravitational potential energy into pressure potential energy. And there's high pressure water at the bottom of the water tower. And you can deliver it and replace it with new water coming down from above. So it's basically a steady state flow situation. And it can deliver a lot of high energy water, which has the energy as it comes out the bottom of the water tower in the form of pressure potential energy, which then goes on to be other things as it flows into your house. All right, those are pipes up and down that are constant diameter. They force the conversions between pressure potential energy and gravitational potential energy because kinetic energy cannot change in those uniform pipes. What's the other possibility? Suppose you let water go up or down in the open air, like a fountain or a waterfall. In a fountain, you're shooting water up from below in open air, and in the open air, the pressure is atmospheric pressure. So the water can't change its pressure when it's a fountain spraying up in the open air. Instead, it has to convert energy, if it does any conversion at all, between kinetic energy and gravitational potential energy. So as water rises in an open fountain where its pressure potential energy is fixed, it converts kinetic energy into gravitational potential energy. It slows down and rises upward and gains altitude. So it's converting one energy to the other. And if you pour water down, say in a waterfall, or the descending part of a fountain, as the water descends in the open air, again, its pressure can't change. So instead, it converts gravitational potential energy into kinetic energy as it descends. So in all, we have 6 possible conversions of energy in the world of steady state flow. And I'll say a few more cents about steady state flow momentarily. When water is in steady state flow, it can convert energy between the three possibilities that it can have: pressure potential energy, gravitational potential energy, and kinetic energy. Nozzles force the conversion between pressure potential energy and kinetic. Diffusers force the conversion between kinetic and pressure potential energy. Uniform pipes, on the way up, they force the conversion between pressure potential energy and gravitational potential energy. On the way down, they force the conversion between gravitational potential energy and pressure potential energy. And the last pair, in the open air, a fountain forces the conversion between kinetic energy and gravitational potential energy on the way up. And on the way down, or in a waterfall, the conversion goes from gravitational potential energy to kinetic energy and down. Okay, so I said I would say 2 cents about steady state flow. The physicists love approximations because the real world finally is often way too complicated to understand in all its gory detail. So you try to simplify things. So steady state flow is conceptually a very simple approximation. In the world of water delivery, most of the plumbing that you deal with doesn't move. It's a stationary environment. At the pumping station where they're actually moving stuff around, there's machinery going, it's not steady state flow. So you gotta be careful in it. The fact that there's stuff moving means that there's stuff that can do work on the water. And often pumps do work on water. Therefore, the energy per drop is not constant. So in the world of steady state flow, you draw a box around the part of the story in which the flow is pretty much unchanging through a stationary environment. And there may be an entry and an exit to this box you've drawn, that outside of which things are not good. Like there is movement and you don't have steady state flow. But within this environment, life is simple. And so we'll start just beyond the pumping station where things are messy and watch the flow through the plumbing of the town, through the plumbing in your house, and everything. And if at the moment you turn on faucets and so on, you allow the water to accelerate. And there is a change in the flow, and that's also not covered properly by the world of steady state flow. But after you've opened the faucet, taking your hands off and let things settle for maybe a second is all you need, the flow settles, and now you've got steady state flow. So the point is, steady state flow is a very good approximation for most circumstances. If the environment's moving, you're going to have to use more complicated, the story's going to be more complicated. A whirligig sprinkler, for example, it's spinning around, that's moving. It's a moving environment that is not steady state flow anymore. But a stationary sprinkler that's just sitting there plopped on the grass, water coming to it through a hose that's sitting still, and the spray going up, steady state flow describes that very nicely. So we use steady state flow to watch the movement of water through the town, up and down the hills. The pressure is rising and falling as the water's descending and rising, and we watch the speed increases, the water goes through in nozzles in your sink, in your shower head, and so on. It all works out very nicely. If finally you need to deal with all the complicated stuff, well, sorry, you're going to have to open the fluid dynamics books more carefully. And the other thing that's going to show up not too distant future is the world of viscosity, the fact that water does rub as it flows and therefore experiences friction-like effects. And the other thing that's going to show up down the road is what's known as turbulence. The flow that I've described so far is not turbulent, it is laminar, meaning that it has streamlines that are well defined. So you can watch the drops entering your story, your drops of ink, bloop, 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 and they work their way through the whole streamline, no problem. If things are swirling white water, the drops don't make it. They get torn apart into shreds. And that also does not fit within the world of steady state flow. So neglecting those complications, the flow of water through plumbing is pretty simple. It's beautifully described. by Bernoulli's equation, which makes the observation that within the steady state flow and along a specific streamline, that's an important caveat, the total energy per drop is constant. So that then is the story of water distribution.